In this video, I'm going to talk a bit about the spherical Bessel functions, and I'm going to go about it in a slightly roundabout way. And so the first thing I want to talk about is what's called the Helmholtz equation. So the second partial derivative of u, which is our function here. And we'll say that that is a function of space and time. So R being just sort of general space. So R could be equal to, if we're in three dimensions, X, Y, and Z, if we're in the Cartesian coordinates, or it could be the polar coordinates, which is actually what we're going to be using. So the radial and then the two angles here. But anyways, the second partial with respect to time is equal to some constant times the Laplacian of our function, where the Laplacian is defined as the divergence of the gradient of our function. Or you can just think about it as the second partial derivatives. And so if we're in, say, Cartesian coordinates, it would just be the second partial derivative with respect to x plus the second partial with respect to y plus the second partial with respect to z, and this is the Laplacian operator that would be acting on our function here. And so, yeah, this is what's called the Helmholtz equation, the Helmholtz equation, sometimes also called the wave equation, and there is the special form of it, which if you've taken like an electrodynamics class, you may recognize as the Laplacian, the Laplace equation here. So that is the del operator of some function being equal to 0, and that tells you about sort of the electric potential. So if this was the potential here, then the Laplacian of it is of this potential is equal to 0. But anyway, that's neither here nor there. So so we are going to think about this if it is not equal to 0. And in that case, what we do is we want to do a separation of variables. So this would actually be after the separation of variables, but we're going to do a separation of variables, where we're going to have u of our function of space and time be equal to the product of some function of space and some function of time. And if we look at just the space part of this separation of variables, then what we end up getting is the Laplacian of our function with respect to space is equal to minus k squared times our function with respect to space. And so the first thing to notice is that this here, this is the special case where k is equal to 0. So so this is if k is equal to 0. But if k is not equal to 0, then what we have here is an eigenfunction problem. And so we have k squared being equal to our eigenvalue, and so an eigenfunction is if we have some operator here. In this case, it's the Laplacian operator operating on our function being equal to some constant times our function. And so in this case, we have k as the eigenvalue, where k is equal to 2 pi over the wavelength, which is what is known as the wave number. And so in this case, the f of r would be the eigen function, and we want to solve this for the eigen function. So this Laplacian operator is our Hermitian operator. The k squared is our eigenvalue, and we want to solve for the eigenfunction. So at different values of k, we want to solve for our eigenfunction. And to do that, we are actually going to do a second separation of variables. And so I said earlier that our r, so our r is equal to the spatial components. And so we could say that f is a function of the radial component and the two angles here. I always forget what these angles are called. There's like the azimuthal angle, and I think like the latitudinal angle or something like that. But anyway, we want to do a separation of variables so that we end up with some function, and I'll call it big R as a function of R, and then, well, I'll just use the y, because that is what we've been using for the functions of these angles here, as of theta and phi. And so now we want to solve for this right here, the radial component of our wave equation up here. The wave equation in space. And so what we will end up getting is some differential equation that will look like r squared. Well, I have it written here for Cartesian components, so I'm just going to switch back to x because it would be different in polar coordinates, but it will look something like x squared dy. Well, I'm using y over here, so I guess I'll use the big R here just to make it clearer that we are looking for the radial component here. Dx plus 2x dr dx, and then plus the x squared minus L times L plus 1 times R, and that is equal to 0. And so we could go through our usual way of solving differential equations using the Frobenius method and so forth, and I'm not going to go through the whole process here, but what we will end up with is two solutions. And these solutions, so Jn of x is equal to pi over 2x, so the square root, times the Bessel function of n plus 1/2. So we are at half integers here rather than at integers of x. And we will also get the other one, but we won't be focusing on this one as much because it goes to infinity at the origin. So it's one that we just set its constants, its arbitrary constants equal to 0 so that it vanishes. but just for completeness, I will show that it is the square root of pi over 2x times our. So this is not uh, the spherical harmonic. So remember, we use the y for the other independent Bessel function, rather, that is a function of x. So we'll be focusing mostly on this one right here. And so this is what is called the spherical Bessel function. So the spherical Bessel function. And so we see that that is in terms of a half integer Bessel function. And if we then wanted to combine this with our spherical harmonics, we would have our wave function as a function of r, theta, and phi being equal to, so we'll have L equals 0 to infinity, and then the summation of m equals minus L all the way to L, and that will be so some constant which is determined by boundary conditions multiplied by our spherical Bessel function multiplied by our spherical harmonics. And so this is the sort of equation that will solve for the wave function here. So this is what the wave function will look like. And so in this case, we are using the spherical Bessel function. So I'll give a little bit of a I guess spoiler here. So the spherical harmonics are going to be used in every solution. I mean, besides like the rectangular wells, but this Bessel function. So the Bessel function is used when we have an infinite spherical potential, and what we'll talk about probably starting in the next video will be the Hermite polynomials. And these are used when we do a one-dimensional harmonic oscillator potential for the oscillator for the Schrodinger equation. So that will look something like this. So if you've watched my videos as I have out as of the recording of this, I've only done solutions for the infinite rectangular potential well and the finite well, and in both of these we have not had to use these special functions. But once we get to this this harmonic oscillator potential well, where it's more of this parabolic function, and these sort of go off to infinity on both sides. So it's still an infinite well. So I guess we could put infinite here, meaning that the particle will never escape this well. It will never become a free particle. And then we will also see that we will have the, I think it's spelled Laguerre, something like that. And so these are if we have a finite spherical potential. And so these are all the the special functions for the radial component of our wave function. So all these special functions when we are solving for r. So I've gone through the Bessel functions here, and as I said, these are what we use when we model it as an infinite spherical potential. The Hermite is when we are doing the sort of simplified 1D, the 1D harmonic oscillator that looks like this right here. Then the Laguerre is when we use a finite spherical potential, which is the way a hydrogen atom is modeled, a hydrogen atom. And so this is kind of what brings together what we're going to be talking about, well, in the previous video, in this video, and then in the next video I will talk a little bit about the Hermite polynomials, and then I will maybe spend a video or two talking about the Laguerre functions. But this here is the spherical Bessel, so I guess we could even put spherical Bessel function here. But anyway, that is what this spherical Bessel function is doing, is in an infinite spherical potential, which is probably kind of hard to picture. So if you can imagine sort of taking this 1D case and sort of putting this into 3D, so that this down here is sort of the center of our sphere. And then as you go in any direction sort of around the sphere, that we have our potential increasing. So the potential increases as you go in any direction from the center of the sphere, such that if we sort of think of the sphere as an onion, each layer of the onion around the sphere. So if we have a sphere, each layer is at the same level of potential, as you would have at a sort of line along here. And so this right here, this line right here is kind of what the center of our sphere would be. And so this right here and this right here would be the potential at some layer of our onion here. And so that is what an infinite spherical potential is sort of supposed to look like. All right, and then if we want to sort of look more explicitly at these spherical Bessel functions, so I have j sub naught here of x is equal to, as I said, it's pi over 2x square root. And since we have n equals 0, since I'm doing n equals 0, then we will have the 0 plus 1/2, so it's the half Bessel function here, so the half regular Bessel function here. And so this will be equal to, if we put this half Bessel function more explicitly, what we will have is we still have our pi over 2x square root, but then putting this explicitly, we have the summation from r equals 0 to infinity of minus 1 to the r multiplied by our factorial times the gamma function of, so the n is 0, so it's 1/2 plus r plus 1, and it's 1 over that. And then we have our x over 2 to the 2r, and then n is 0 plus half, so it's 2r plus 1/2. And so if we know that our gamma function if we have r plus 1 plus 1/2 written out explicitly, is going to be the 2 to the 2r plus 2 times r plus 1 factorial. Then up here will be 2r plus 2 factorial. And because of that half in there, remember in a couple videos ago I said that the gamma function of a half is equal to the square root of pi. So we will also have a square root of pi in here. And so if we write this out explicitly, and remember the gamma function here is in the denominator, so this is actually going to get flipped over, then what we have is we have our j naught of x being equal to, and I'm going to write this a little bit differently because we're going to be canceling out a bunch of stuff. So I'm going to put 2 to the 1/2 power, which is the same as square root, and x to the 1/2 multiplied by the summation from r equals 0 to infinity of minus 1 to the r times, and we have our r factorial times 2r plus 2 factorial square root of pi. And then in the numerator we have 2 to the 2r plus 2 times r plus 1 factorial, and then we still have our x, and I'm going to write this way. So 2r plus 1/2 over 2 to the 2r plus 1/2. So I've just kind of distributed this exponent to both of these here. And what we will see is that we this 2 here could be written as 2 to the 2r times 2 to the 1/2. And so this 2 to the 1/2 times this 2 to the 1/2 will make it into 2 to the 2r times 2. And so we have this 2 to the 2r here, which is going to cancel out with this 2 to the 2r. Then this 2 will cancel out with the 2 to the 1 here. So this will just end up being a 2, while both of these go away. This x to the half here will cancel out with the x to this half here. So this goes away. This square root of pi will cancel out with this square root of pi. Now we will have this be equal to, after all those cancellations, so this whole thing has been canceled out. So now we just have the summation from r equals 0 to infinity of -1 to the r, and we still have in the numerator 2 times r plus 1 factorial, r factorial times 2r plus 2 factorial, and then that is times, we now have x to the 2r, because that half got canceled. Well, we see here that if we have r plus 1 factorial over r factorial, that will just cancel out that'll cancel out this r and the factorial, because it's essentially like having, if we had 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1, where 4 would be like our r and 5 like our r plus 1. We just cancel out all of these and end up with just the r plus 1. And so that will give us, so we are left with the 2r plus 1, So that would be the same as 2r plus 2, which we see will cancel out with the highest of this, making that into 2r plus 1 factorial. And so after all that canceling out, what we end up with is the summation from r equals 0 to infinity of minus 1 to the r, and then we can write this as 2r plus 1 factorial and x to the 2r. But if we sort of multiply both sides, or well, multiply all of it, I guess you could say if we multiply all of it by x over x, which we can do because that just equals 1, what we end up with, so I'll pull out the 1 over x here outside the summation from r equals 0 to infinity, we end up with 2r plus 1 factorial and then x to the 2r plus 1. And this you may recognize as the series for sine of x. And so what we then end up with is sine of x over x. And so this is the j naught of x. So the first, or I guess zeroth spherical harmonic is sine of x over x. All of these spherical Bessel functions end up being in terms of these trigonometric functions, and I will show you that on the Wikipedia page. So these are the first three of our j, and we also see that we can have the y ones here as well. But j naught is sine of x over x. If we did it for 1, if we went through that process for 1, we'd end up with sine of x over x squared minus cosine of x over x. For 2 is 3 over x squared minus 1 times sine of x over x minus 3 cosine x over x squared, and so on and so forth. And so if you actually plot these, so these are the spherical, here over on the right side on the top are the spherical Bessel functions of the first kind, so that is our j version here. And you can see that it's pretty much the same as our Bessel functions, so you can actually see those up here. So these are the regular Bessel functions plotted here as a function of x. So the spherical ones look very similar. These are the spherical Bessel functions of the second kind, which are the y versions. You can see these sort of blow up, or I guess you could maybe say implode towards negative infinity, where these are finite at the origin, and so that's why we focus mostly on these Bessel functions rather than the Bessel functions of the second kind. And so anyway, that is what the Bessel functions are. And once again, to kind of interpret it is you could say that, well, I will say that the spherical harmonics tell you what is happening on the surface of a sphere at some fixed distance from the origin, where the radial equation is telling us if this is the origin of our sphere, we want to know what's happening as a function going out to the surface. And so you could say that each of these x's is some distance from the center of our sphere. So the origin 0 would be the center of the sphere. And so the value of the wave function as a a function of the distance from the center of the sphere looks like what these are, looks like these functions here. And so you can see that these have zeros. They cross zero at different places. And if we wanted to interpret this sort of like an atom, uh, you know, if we had our proton here in the center, then we would look at those zeros as the nodes our of our orbitals. And so if you've taken like a chemistry class, you will know that that if we have a a 1s uh, a 1s orbital, then it's a sphere like this and it has no nodes. But if we go up a level, then we know that it has a node. Probably even that out a little bit more. A node here, and then sort of the end or the edge of our density. And so we can see here that as we go from the nucleus to this node here, we are in the positive phase, and then after this node we go down into the negative. And so that's what that would look like here. So we're in the positive, and then we go down into the negative. And then we would set this zero here as the boundary condition. And so that is sort of a way of interpreting these Bessel functions. And it'll be the same for the Laguerre functions as well. And so, yeah, that is the spherical Bessel functions. I hope you found this video somewhat enlightening on the subject of Bessel functions, and I will see you in the next video.